Hello and welcome back to Introductory Astronomy. Today we're going to talk about galaxies and dark matter. Now some galaxies are bright and splendid, like the 5 big ones in this image, which is known as Stephan's quintet. Others are dim and distant, like several that appear smaller in the background. One member of this group, NGC 7320 on the upper left, is actually 7 times closer to the Earth than the other 4, which are in the process of colliding. Mergers and acquisitions are common among galaxies, but astronomers still don't fully understand how galaxies formed long ago. In this chapter, we're going to talk about dark matter in the universe, galaxy collisions, galaxy formation and evolution, black holes in galaxies, and the universe on larger scales. Now, we talked about the rotation curve of our own galaxy, and other galaxies, of course, have their own rotation curves, and they're similar to ours. And rotation curves are very useful because they allow for measurement of a galaxy's mass. If we take a look at frame A, by observing orbital velocities at different distances from the center of a disk galaxy, we can plot a rotation curve for the galaxy. This is M64, the quote-unquote evil eye galaxy, which is about 5 megaparsecs distant. In frame B, we have rotation curves for some nearby spiral galaxies that indicate masses of a few hundred billion times the mass of the Sun. The corresponding curve for our own galaxy is marked in red for comparison. Another way to measure the average mass of galaxies in a cluster is to calculate how much mass is required to keep the cluster gravitationally bound together. In frame A, we have a binary galaxy system, and galaxy masses can be estimated by observing the orbit of one galaxy about the other, just like we did for masses of binary star systems. In frame B, we have the mass of a galaxy cluster can be estimated by observing the motion of many galaxies in the cluster and estimating how much mass is needed to prevent the cluster from flying apart. Now, galaxy mass measurements show that galaxies need between 3 and 10 times more mass than can actually be observed to explain their rotation curves. The discrepancy is even larger in galaxy clusters, which need 10 to 100 times more mass than what we actually observe. Thus, the total needed is more than the sum of the dark matter associated with each galaxy. There is evidence for what is called intracluster superhot gas, about 10 million Kelvin, that is located throughout clusters and is densest towards the center. Here we have the galaxy cluster X-ray emission. In frame A, we have a superposition of infrared and X-ray radiation from the distant galaxy cluster Abell 1835. The X-rays are shown as a fuzzy bluish cloud of hot gas filling the intracluster spaces among the galaxies. Frame B is a longer infrared exposure of the central region, showing the richness of this cluster, which spans about 1 million parsecs. Images like this demonstrate that the space between the galaxies within galaxy clusters is filled with superheated gas. These head-tail radio galaxies' lobes are being swept back, probably because of collisions with intracluster gas. In frame A, we have a radiograph in false color of this head-tail radio galaxy. In frame B, we have the same radio data in contour form superposed on the optical image of the galaxy. Astronomers reason that this object is moving rapidly through space, trailing a tail behind it as it goes. It is believed this superhot gas is primordial, dating from the very early days of the universe. There is not nearly enough of it to be the needed dark matter in galaxy clusters. Let's talk a little bit about galaxy collisions. The separation between galaxies is usually not large compared to the size of the galaxies themselves, and galactic collisions are frequent. This is the Cartwheel Galaxy on the upper left, and it appears to be the result of a collision that has led to an expanding ring of star formation moving outward through the galactic disk. The offending galaxy might be one of the smaller objects at right, or as implied by recent radio observations of loose linking gas, it might have been another galaxy now further away and beyond the field of view. This is a false color composite image combining 4 spectral bands: infrared in red from Spitzer, optical in green from Hubble, ultraviolet in blue from Galaxy, and X-ray in purple from Chandra. Here we have an encounter between 2 spirals, NGC 2207 on the left and IC 2163. And it has already led to bursts of star formation in each. Eventually the two will merge, but not for 1 billion years or so. The starburst galaxies show evidence of massive recent activity, clearly the result of a collision. So we have an interactive galaxy pair, IC 694 on the left and NGC 3690. And it shows starbursts underway in both galaxies, which is why we have that bluish tint. Such intense short-lived bursts probably last for no more than a few tens of millions of years, which is a small fraction of a typical galaxy's lifetime. Here we have the Antennae galaxies, which collided a few tens of millions of years ago. The long tidal tails, the black and white image on the left, mark their final plunge. Strings of young, bright superstar clusters, in the image in the center, are the result of violent shock waves produced in the gas disks of the 2 colliding galaxies. Frame B is a computer simulation of the encounter, and it shows many of the same features of the real thing, and this strengthens the case that we really are seeing a collision in progress. If you take a look at frame A here, we have the present view of galaxy formation, which holds that large systems were built up from smaller ones through collisions and mergers, as shown in the drawing. In frame B, in this photograph, we have one of the deepest ever taken of the universe, meaning we're looking at the faintest and most distant objects, and this photograph provides quote-unquote fossil evidence for hundreds of galaxy shards and fragments up to 5,000 million parsecs distant. In frame C, we have enlargements of selected portions of B, which reveal rich, meaning billion star clusters, all lying within a relatively small volume of space, about 1 megaparsec across. Their proximity to one another suggests that we may be seeing a group of pregalactic fragments about to merge to form a galaxy. The event's picture took place about 10 billion years ago. This Hubble Deep Field view shows some extremely distant galaxies. The most distant appear irregular, supporting the theory of galaxy formation by merger. And this is a picture of the Hubble Deep Field North, and it shows some of the galaxies that lie more than 1,000 million parsecs from the Earth. This particular image was made with an exposure of approximately 100 hours, and it captured objects as faint as 30th magnitude. As in the previous figure, deep in this context implies faint, meaning that we're looking at objects far away, and of course as they were long ago. Redshift measurements, as denoted by the superposed values observed at the Keck Observatory in Hawaii, indicate that some of these galaxies lie well over 1,000 megaparsecs from the Earth. The field of view is about 2 arc-minutes across, or less than 1% of the area subtended by the full moon. Galactic cannibalism. Here we have a dramatic glimpse of a large and massive galaxy under assembly by the merging of smaller, lighter galaxies. This is the way most galaxies probably developed in the earlier universe, by means of a bottom-up scenario that hierarchically built really big objects by merging star-rich building blocks. This image captures a formative process that occurred about 10 billion years ago, only a few billion years after the Big Bang. The bigger image highlights a region at upper left, in the white box, cataloged MRC 1138-262 and nicknamed the Spiderweb Galaxy. The inset shows more clearly dozens of small galaxies about to merge into a single huge object, in fact altogether one of the most massive galaxies known. The Milky Way Galaxy also contains stars in its halo that appear to have been the result of the capture of smaller galaxies. This illustration depicts the breakup and dispersion of the contents of an incoming star-rich galaxy companion captured by our own Milky Way Galaxy. Such streams of stars, all in similar orbits and having much the same composition, are found in the halo of our galaxy today. Eventually, the smaller galaxy dissolves within the larger one, a case of the little one being digested, much as other dwarf companion galaxies were probably consumed by our galaxy long ago. So galaxies can change their shapes long after their formation. In this computer-generated sequence, two galaxies closely interact over several 100 million years. The smaller galaxy in red has gravitationally disrupted the larger galaxy in blue, changing it into a spiral galaxy. Compare the result of this supercomputer simulation with a photograph of M51 and its small companion. Our own Milky Way Galaxy and the Andromeda Galaxy will collide in about 4 billion years, and I put a link right there to space.com that shows a short video of the collision simulation, and it spans 8 billion years. So check it out. It's only a couple of minutes long. Here we have the general galaxy merger scenarios. When comparably sized galaxies come together, the result is probably an elliptically shaped galaxy, as their original arms and disks do not likely survive the encounter. By contrast, if a large spiral absorbs a smaller companion, the probable result is merely a larger spiral, with much of its original geometry unchanged. We covered chapter 25.1 through 25.3. You should be able to describe some of the methods used to determine the masses of distant galaxies. Be able to explain why we think most of the matter in the universe is invisible, and discuss some theories of how galaxies form and evolve.